our role within Ariadne is to develop new metasurfaces for novel wireless communication systems. Metasurfaces can be described as passive devices which can reflect or refract the electromagnetic field and process it, for example, gain it, in order to establish this wireless channel between two devices, and functionality of this metasurface can be theoretically ideal. People working with metasurfaces usually apply the so-called phase gradient method. However, it is known that even theoretically this method has a list of limitations and disadvantages. For example, it is limited on its angular performance, and it is known that even theoretically it's impossible to design a metasurface using this method which can grant you ideal performance for large angles. But in our group there was developed a method which allows to design a metasurface of ideal performance. I'm not going to go deeply into details, but you can always address to the Ariadne project website, where you can find a list of publications of our group where we describe this method in more details. Anomalous reflection is one of the fundamental but advanced functionalities of metasurfaces, where we can control the direction of the reflected beam. And based on these studies, we can develop new devices with new functionalities. For example, splitting of the incident and reflected beam into several directions, and other new and interesting purposes depending on the formulated problem. We start from the theoretical solution of the physical problem in order to satisfy the required functionality of the metasurface. For example, as in our case, we're dealing with some particular incidence angle and redirection of this signal in the desired direction. Then we are switching to the electromagnetic simulations and widely apply commercial engineering software for electromagnetic simulations. The third step is the so-called implementation. This is a bridge between the fundamental theoretical solution and real-life application. Then we are doing microfabrication of these metasurfaces and validate it within our laboratory facilities. At the end, we're sending the metasurfaces to be used in the demonstrator. As with any other R&D problem, we always meet with new interesting physical effects which we have to describe and adequately define how to make use out of them. Another important part of the difficulties which we meet, I think, is the manufacturing. Those problems which we can feel with our hands. And for example, when we understood that we have to use a very thin and fragile dielectric layer, we had to define where to get it, how to prepare these kind of thin substrates, how to process them with the tweezers and your hands, and so on and so forth. Those I have to note and thank here my colleagues from my research group, Shucheng Wang, Anna Diaz-Rubio, Victor Asacchi, and Professor Sergei Kosulnikov, because they are always doing the great impact in order to have progress within this Ariadne activity. Now we passed 2/3 of the planned Ariadne schedule, and we already published many interesting scientific journal papers and presented our results at different conferences, and we are going to do more at the rest of the period. And I'm sure these scientific results, first of all, will be quite interesting and will make an impact for the community who are working with the metasurfaces. And on the other hand, I'm sure that in the near future, these results will be implemented for our everyday life and will make it more comfortable. In particular of our activity, we are going to prepare 3 metasurfaces for 3 given frequencies, and these metasurfaces will be used in the indoor line of sight demonstrator.